Video 2 of day 15, another case study of generalizing the induction hypothesis. First, I want to introduce a concept that really I should have shown you when I introduced the injection tactic, because it's kind of the reverse of it. Though honestly, it's something we could have seen on day 1, though I don't know that we would have really appreciated it. By day 1, I mean day 11. Day 1 of proof. So the theorem F equal says that, hey, if two things are equal, then giving them to a function yields equal results. This, in some sense, is the actual definition of equality. Like, when are things equal? They're equal when they behave the same in all contexts, right? That's a notion of equality. That notion of equality is due to Wilhelm Gottfried von Leibniz, whose name you might know from calculus. Leibniz and Newton were frenemies. Maybe even, well, they exchanged letters. Frenemies, enemies, tough to say. But anyway, he was super involved in calculus development, but also Leibniz was like a really important thinker just in analytic philosophy in general, and so his concepts of equality persist today. So in any case, the basic idea is, look, x equals y, so we can substitute y for x, and then it's just equal. Right. It turns out this is a really useful tactic for just like you get in goal states and you can like say, well, the way I'm going to show that these two functions applied to things are equal is the things I'm applying them to are equal. Okay. So the proof I want to show you is this one. Um, I'm going to start out doing the proof the right way, and then we'll go back and we'll look at what it looks like the wrong way. So the right way here is to have a generalized induction hypothesis. So, okay, let n be given. We'll go by induction on n. In the base case, we have this sort of not yet fully introduced state. So let's introduce m and some equation h. Okay, great. So we know there's a natural number m. We know EQB 0, m equals true. We need to know that 0 equals m. So let's go by cases on m. Okay, well, if m is 0, then it's very easy to show that m is 0. If m is not 0, well, okay, well, our goal looks bad, but also, so does our context. Let me show you again. So EQB 0 s of m prime is definitely not true. So we can blow it up. Okay, what about here? Intros MH again. If you're on team semicolon, like after a generalized induction is a great place to do your intros with a semicolon because it just does it for you in both settings. Here you can actually go farther. Okay, cool. So let's see where we are. We need to show that successor of n prime is equal to m. We know that s of n prime is equal to m according to our function EQB. And we know that if n prime is equal to any number m, right, this universal quantification here, then n prime is really equal to m. Okay, great. So let's see what the story is with m. Maybe just to vary things, we'll do it here in an intros pattern. Why not? You know, mix it up. Okay, so well, if m is 0, I don't know, that h looks suspicious to me. Yeah, beautiful. Right? Then there's no way EQB could have said they're equal. Okay, now, if it doesn't, well, if you remember how EQB is defined, it tries to just sort of strip a successor off of each side. So if we simple, we should get perfect, just that n prime equals m prime according to EQB. But now our IH can apply, right? Because this is for all m, so let's just like pick m prime here. So great. Right? If we want to be super explicit, we could say something like this. Doesn't win us anything. Coq can guess it itself, but I just want to highlight that's the thing being chosen. So great. So now if n prime equals m prime, well, a nice thing we can do is something like this. Right? So this is the lemma I just proved above. Basically, I'm saying, look, s of n prime equals s of m prime because n prime equals m prime. So now I could say apply h. Okay. Let me go back and show you a different way we could do this. Maybe you're not a huge fan of this forwards reasoning I'm doing. We could instead have said up here, apply f equal. And then here we could have said apply IHN prime. And again, Coq will be able to guess m prime for m because it's here in the conclusion. So now we're just doing this backward reasoning, right? And now we could say simple in h, apply h. I don't know which of the, sorry. I don't know which of these two proof scripts you like better. I think this one's a little simpler, right? The fewer in tactics is maybe easier to track, but it really, I think, doesn't particularly matter. This simple in H is not, strictly speaking, necessary. But, you know, kind of your mileage may vary. Okay, let's see what happens if we do it wrong. Oop, no need to shout. Okay, so well, we no longer need this. And then all this should stay the same. But then when we get here, ah, excuse me. Gotta comment it out. Probably supposed to destruct M as M prime. That's what I get for using fancy tactics. Okay, that all stays the same. But now look at our IH. We're in that bad situation again where it's stuck in the past, right? It's living in this like concrete S prime. So if you did F equal, you'd actually be able to make some progress, but then you'd get here and it would say, thank you, Emacs. It would say, these don't match. Your IH lets me show that N prime is equal to SM prime, but you need to show something different, so I'm sorry, bud, it's not going to work. Pause a sec so you can take notes. Let me get it back to the old way. So here's maybe a very succinct way of doing it. Oops. A downside to this semicolon approach, which I'm showing just for giggles, is that there's no like these two cases here are both base case, and that's not maybe super obvious, right? And then these cases here, we're starting uh, the inductive case. So maybe not the clearest, but let's just round it out. Okay. If you don't like this proof, this is like me just on some level just showing off. If you don't like this proof, that's totally fine. Go back, rewind the video. You can look at the other way that we did it. Okay, so what's cool now, I just want to like mention, like, so we talked about all this reflection stuff on day 14. Now we can finally start reflecting our more interesting equalities, right? EQB is correct. You know, we got it right forever ago, day 2 or whatever it was. Like, we really nailed it, actually. If EQB says two things are equal, then they really are equal. I want to highlight something about the structure of this proof. One, we're just using lemmas. Two, okay, let it be given. In one direction, we just use the lemma, right? We had to do this general induction to prove it correct. In the other direction, it's like a little bit like F equal, right? We say, well, if N1 and N2 are really equal, then we can just say that EQB is reflexive. Right? Maybe you remember this proof from forever ago that like we just know that that's the case. So we go there. This structure of like, okay, in one direction you prove that your function implies real equality. In the other direction, you only need to prove reflexivity is very common. This is sort of the structure of a reflection proof for equality. Wanted to stress that. Okay, anyway, cool. This generalized induction seems to be pretty powerful. It was really key for us being able to prove this lemma, which was key for us being able to reflect equality. So it's definitely an important technique. In the rest of the day, we're going to spend most of our time talking about like when you do this and different ways of doing this, of getting these nice varied or general inductive hypotheses. And then at the end, we'll have one more sort of side topic that's leading up to day 16. All right, talk to you soon.